This is an unbelievable way to memorize every single detail of the Krebs cycle, and I promise you have never seen this before. We're going to use this famous mnemonic, but we're also going to go over how to memorize the byproducts and even the structures for each molecule. And then at the end, I'm going to give you a new mnemonic to help with that. The famous mnemonic is used to help you memorize the names for all the molecules in the cycle because the first letter of each word lines up with the first letter of each molecule. But in case you didn't know, you can also use it to memorize the enzyme names. Starting with citrate synthase, the first letter of each word in that mnemonic does line up with these enzyme names. The one exception is aconitase, which fits in between can-I, and you'll have to just remember that one on your own. There's also not an enzyme that starts with O, so you can just ignore that letter. Now we're going to look at how can we remember the byproducts and the structures of all of these molecules. We're going to use an understanding of what these enzymes and byproducts imply about the change that happens from one molecule to the next. And then at the end, I'm going to give you a mnemonic to make that even easier. Starting with citrate, this one is the only molecule that you're going to have to remember without many tricks to help you. The only one I can give you is that we know it's a combination of acetyl-CoA, which is a 2-carbon molecule, and oxaloacetate, which is a 4-carbon molecule, so citrate has to be 6 carbons. It is also a symmetrical molecule with this carbon serving as the center. If you have citrate memorized, then you can rely on a lot of these tricks that we'll talk about to help memorize the change that happens from each molecule to the next. And remember, there will also be a mnemonic at the end to help with that. For isocitrate, the term iso is used because it's an isomer of citrate, so we know that it has to have all of the same atoms. What I like to add to that is that the iso is telling us that this OH group gets moved to its own carbon and becomes isolated. And that's the only change that happens from citrate to isocitrate. After this, we encounter our first dehydrogenase enzyme. And every time that we see a dehydrogenase, we know that NAD+ or FAD is going to come in and get reduced. And anytime one of those gets reduced, something has become oxidized, which is a huge help to knowing how the molecule's structure changes. When you look at isocitrate, an obvious candidate for oxidation is that OH group. And anytime an OH group gets oxidized, it turns into that carbonyl group, which is exactly what we see in alpha-ketoglutarate at that exact same position. There is also a loss of CO2 during that step. And if you look on isocitrate, there is a CO2 group right here attached to that middle carbon. But on alpha-ketoglutarate, that group is gone, which is explained by the loss of that CO2 group. In the next step, we have another dehydrogenase, so we're looking for a similar thing to happen. This is one of the more complicated steps, but we're going to use the relationships between all three byproducts here to help us remember what happens. NAD+ is going to take the hydrogen from the coenzyme A group. That's going to leave a lone pair on that sulfur, which will then allow that sulfur to act as a nucleophile and attack that carbonyl carbon. That attack is going to kick off this entire CO2 group here, which is explained by the loss of the CO2. And then when you look at the product, succinyl coenzyme A, we see that coenzyme A group attached to that carbonyl carbon that it attacked. So while this step is a little more complicated, understanding those relationships can make it a lot easier to remember. The next step is much more simple. We see the loss of that coenzyme A group that was just added. And sure enough, the only difference between succinyl coenzyme A and succinate is that instead of the coenzyme A group, we just see an oxygen attached to that carbonyl carbon. Don't worry about the production of a GTP here because this will be addressed in the mnemonic that I'll give at the end. Next, we have another dehydrogenase and an FAD that accompanies it. The FAD is getting reduced, so we're looking for what gets oxidized. On the molecule succinate, there's really only one thing that can be oxidized, and that is the single bond between those two middle carbons. When a carbon-carbon bond is oxidized, it will turn into a double bond, just like what we see in fumarate. Now, fumarase adds the H2O, and when you add an H2O across a double bond, you're going to add an OH group on one of those carbons, and then a hydrogen on the other carbon, and that hydrogen just isn't drawn in. Our last dehydrogenase comes in, and it's accompanied by an NAD+, and hopefully you can predict that something has to get oxidized, and the obvious candidate is the OH group on the malate, and we do see that turn into a carbonyl group. Now finally, for that mnemonic that's going to help you remember all of these byproducts. The first letter of each word in this mnemonic corresponds to the first letter of a byproduct. Starting at isocitrate dehydrogenase, we have campers never cook near cemeteries because creepy ghosts fly high nearby. Once again, use this mnemonic to help you remember the byproducts for each step, and then a combination of the byproducts and the enzyme names are going to help you remember the structures for each one of these molecules. And the molecule and the enzyme names are already covered by that first mnemonic. Now try to recall all of the Krebs cycle, and if it works, share this video with someone else who might need it.